Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Laminar Flow of Generalized Newtonian Fluids between Parallel Plates and Along Inclined Surfaces. Till now what we have seen only pipe geometry. For the circular pipe geometry, infinitely long circular pipe geometry, when L by D is very large and then laminar flow conditions are existing, how to obtain the volumetric flow rate, how to obtain the velocity profile, average velocity, maximum velocity, volumetric flow rate, friction factor, etc. Those things we have seen for the laminar flow conditions when the geometry is pipe or circular cylinder. Then we have also seen for the same circular cylinder or pipe geometry, if the flow is under the transition or turbulent flow conditions, how to get the velocity profiles, how to obtain the friction factors, if it is possible to obtain analytically, how to get them, if not, what are the correlations or empirical correlations existing for these friction factors, etc. Those things we have seen even for the transition and turbulent flow conditions, but when the geometry is the pipe geometry. So, now what we do this and the next couple of lectures we will be taking different geometries other than the pipe geometries. Let us say in today's lecture we are going to take two geometries. One is the parallel plates. If a fluid is confined between two infinitely long parallel plates, then if the flow is under laminar conditions, how we can obtain the velocity profile for a given generalized Newtonian fluid. Generalized Newtonian fluid in the sense any time independent non-Newtonian fluids which can reduce to the Newtonian behavior under certain limiting conditions that we know. So, that is power law fluids, Bingham fluids, etc., or viscoplastic fluids, generalized ones. So, these kind of fluids we are going to study now for the flow between parallel plates, infinite parallel plates. Another geometry that we are going to take is inclined surface. If you have an inclined surface and then along that inclined surface, if the material is flowing down because of the gravity, so then how to obtain the velocity profile for that geometry and then how to obtain the volumetric flow rate of a certain fluid flowing down the inclined surface, that is what we are going to see, and then we wind up the class with an example problem as well. So, the methodology is same whatever we have done for the case of pipe flow. So, that is we have to draw the geometry and then make out or list out all the assumptions or restrictions if we are solving the problem for under laminar flow conditions, and then simplify the continuity equation, momentum equation, so that you get a relation between shear stress and the pressure drop or whatever the driving force that is causing for the flow to occur. So, that relation we have to obtain. Once we have that relation for the shear stress, then getting the velocity profile, volumetric flow rate is etc., are just a kind of a mathematical simplifications. So, that is what we are going to do now for the case of infinite parallel plates, flow between infinite parallel plates. So, first we take power law fluids for this geometry. We are going to take Bingham plastic fluids as well. So, but whether it is power law fluid or Bingham plastic fluids, as long as the flow is the laminar symmetric one dimensional flow, then what we can have a kind of analysis simplification of momentum equations. Up to that point it is going to be same, right. So, because up to getting the relation for the shear stress, we are not incorporating any information about the rheology of the fluid. So, till that point, whether it is a power law fluid or Bingham plastic fluids, the methodology is going to be same. So, schematically if you see, you have two infinite parallel plates which are separated at a distance 2h. So, the center axis whatever is there, that we are taking y is equals to 0. So, the geometry we are taking y is equals to 0 at the center of these two infinite parallel plates. Okay. So, that is the central axis we are taking. So, now between these plates actually in general in real life applications, these plates are infinitely long, but the gap between these two plates is in general very small. It may not be very small that it is negligible, that you take the viscous dissipation etc., also into the consideration. In fact, those kind of things would also be there, but however the gap between these two is in general very small. So, that let us say in the z axis, in the z direction, the length of these parallel plates, if it is L. So, L by h if you do, it is going to be very long, very large. If you take L by h value for this kind of geometry, in general you are going to have that L by h very large value. When you have this L by H kind of values or L by D kind of values that we have in pipe geometry. So, here L by H, if you have a very large value of L by H, then you can say that flow is a kind of fully developed. Okay. So, this is the geometry. So, now the material whatever the fluid that we are considering here. So, let us say now here power law fluid that is flowing between these infinite parallel plates, and then that flow is because of the pressure gradient. Okay. Obviously, because of the pressure difference only the flow is taking place, otherwise the how the flow will take place, because this is a horizontal plate. So, gravity is also not there. So, some external force has to be there, so that the flow takes place. So, then that external force is because of the pressure difference that we are generating or maintaining in order to have a required flow rate of this fluid whatever we are confining between these two plates. Okay. So, this is geometrically this is what we are having now. So, now what we do, we have to list out the assumptions, we have to list out the assumptions, right. Before seeing the assumptions, if it is a laminar one dimensional flow, so what we see, the flow is dominated in which direction, it is dominated in the z direction. So, we are going to have only Vz velocity, right, and then that flow is confined between y is equals to minus h to y is equals to plus h. So, the whatever the Vz component of velocity is there, that is varying in the y direction. So, Vz as function of y, that is what we are going to have in this case, whereas the Vx and then Vy are going to be negligibly small compared to the Vz. So, then Vx, Vy we can cancel out, or we do not need to consider, because Vz is dominating compared to Vz magnitude wise, Vx, Vy are going to be negligible, we can neglect them. And then what are the stress component are going to exist here. So, there are 9 stress components any flow field if you take in general. So, out of which here in this case, since the flow is in the z direction and then that flow is varying in the y direction, so we are going to have only tau yz component of the shear stress. Rest all other we are not going to have, since it is a since the material is a time independent non-Newtonian fluid and there are no elasticity. So, normal stresses are altogether not existing, and then out of the other tau xz, tau zx etc., all those components are negligible. So, what we are going to have, we are going to have only tau yz. So, what we have to do, we have to, when we do solve this problem, the primary aim is to get what is this expression for tau yz, in this case tau yz, in the case of pipe flow it was tau rz. If you have the other geometry like inclined surface, we are going to see, so there you may be having tau xz or something other geometry depending on the geometry and then coordinate system how are you selected. So, if you have that information about the shear stress, then after that everything is straightforward mathematical simplification to get the velocity profile, to get the volumetric flow rate etc., or even friction factor, right. So, the primary thing that we are doing in this kind of problem solving, first we are getting the expression for tau yz or shear stress, whatever the shear stress distribution is there, that expression we are going to get in general first. How we get that one? Simply by simplifying the momentum equation, right. Simply by applying the constraints of the problem to the momentum equations, generalized to momentum equations. Then after applying those simplifications or restrictions to these momentum equations, we will be having an expression for a shear stress. Upon solving that expression for shear stress, you will be getting the velocity profile. So, for this problem, what are the assumptions? Flow is steady, obviously under those limitations only we are studying, and then laminar, so that and then symmetric. Laminar flow conditions we are taking, right. So, symmetric in the sense whatever the flow distribution is there between y is equals to 0 to y is equals to plus h, the same distribution we are going to have between y is equals to 0 to y is equals to minus h. Okay. The fluid is incompressible and then flow is fully developed because L by H is very large, or the lengthwise these parallel plates are very long, the gap between these two parallel plates is very small. So, because of that one we can happily have a fully developed flow conditions under as a kind of valid condition. Okay. 3-dimensional way if you see, so the width of the plate in the x direction, that is going to be W. So, that is going to be useful when you do the volumetric flow calculations. So that is what now here. So now another assumption is that it is a rather assumption reality, we are having horizontal plates, so then gravity is negligible. Then isothermal conditions, there are no reactions, there are no mass transfer conditions, etc., standard things, and then flow is dominated in the z direction. So, Vz component is existing, that Vz component of velocity is varying in the y direction. So, Vz is function of y, that is only existing, Vx, Vy are going to be very small compared to the Vz. So, then we can take them as 0. So, now having enough understanding about the geometry and then restrictions of the problem, what we can do, we can go to the simplifications of momentum and then conservation of mass and conservation of momentum equations. So, we are going to simplify the continuity equation, right, then we are going to simplify the momentum equations. So, the geometry is in Cartesian coordinates. So, the continuity equation in Cartesian coordinate is given here. So, this is the continuity equation that we have already derived in the Cartesian coordinates. So, it is a incompressible as well as steady flow. So, then first term is 0, Vx is negligible, Vy is negligible, and then flow is fully developed flow. Vz is existing, but flow is fully developed. If the flow is fully developed, that means any variations in the flow properties along the flow direction would be negligible. So, dou by dou z of Vz is 0. So, then continuity is satisfied. Okay. So, what does it mean by whatever the assumption that we have taken or constraints of the problem that we have listed out, they are consistent. They are consistent if we are getting the continuity equation is being satisfied, then that is what it mean by. So, if continuity equation is satisfied by applying the constraints of the problem, that means the whatever the listed out constraints are there in the previous slide, they are reliable, physically acceptable. Then momentum equation, first we see the x component of momentum equation. So, this is the momentum equation. So, now we apply the constraints, steady problem. So, first term is 0, Vx is 0, Vy is 0, Vz is existing, but Vx is 0. So, then left hand side all the terms are cancelled out. Pressure we do not know in general, pressure limitations in general, any of the such kind of problems we do not know. So, then we just keep it as it is, right. So, only tau yz is existing. So, all these components are of shear stress are negligible. So, then we can strike out, and then we have not taken any gravity because the geometry is horizontal geometry. So, then what we get, dou p by dou x is equals to 0, that means pressure is not function of x direction, pressure is not varying in the x direction, right. Similarly, y component of momentum equation, if you simplify, so because of the steady state, this first term is 0, Vx is 0, Vy is 0, Vz is existing, but Vy is 0 as well as dou by dou z of velocity components are 0. So, then this term is also 0. So, here also left hand side altogether all the terms are very small, that we can take left hand side is equals to 0. Now, pressure we do not know what it is, we have only one shear stress. So, then this is tau xy is 0, tau yy is 0. Because of the fully developed flow condition, this is 0, and then the gravity is not there. So, this is 0. So, then here also we get dou p by dou y is equals to 0. So, that means pressure is not function of y as well. Now, z component of momentum equation, if you simplify, so steady state term, this is 0, Vx is 0, Vy is 0, Vz is existing, but it is not function of z, it is function of y only. Why it is not function of z? Because of the fully developed flow. Because of the fully developed flow, dou by dou z of velocity component is 0. Pressure we do not know, so let us leave it as it is, and then this tau xz is not existing, tau yz is existing, and then tau yz is function of y, right. Shear stress is 0 at the center between two parallel plates, and then it is maximum at the wall. So, from center to the wall or any of the top plate or bottom plate, when you move in the y direction, that is y is equals to 0 to y is equals to plus h, or y is equals to 0 to y is equals to minus h, the shear stress is varying. So, that is the reason this dou by dou y of this one we cannot cancel out. Okay. And then this shear stress component is anyway 0. So, then we can cancel out, and then the gravity we are not taking because of the horizontal geometry. So, then here what we get, left hand side again all terms are negligible, that we can take left hand side is equals to 0, right hand side we have two terms remaining, that is dou p by dou z and then dou tau yz by dou y. So, dou p by dou z is equals to dou tau yz by dou y, this is what we have. Now, coming to the case how to solve this equation, because left hand side it is function of z and then y, right hand side is function of y. But however, already we have seen that pressure is not function of x and y. That means, for the when you for the right hand side term, whatever the dou p by dou z is a constant one, because right hand side term is function of y, but left hand side term whatever the pressure is there, it is not function of y. We have already seen by simplifying the x and y components of momentum equation. So, with respect to the right hand side term, left hand side is constant. Similarly, this tau yz, it is not changing in the z direction because of the fully flow conditions, right. So, it is changing only in the y direction. So, when you take the left hand side term, when you take the left hand side term for the solving or integrating it, so right hand side term is going to be constant for it. So, that means these two terms individually we can take and then equate to some constant and then integrate them. So, let us say that constant you can take C1 or anything like that. So, that means dou p by dou z, if you take let us say constant C1, then P is C1z plus C2, apply the boundary conditions at the z is equals to 0, let us say if you take P is equals to P naught, then C2 you get P naught, at z is equals to L, if you take P is equals to PL, then you will get C1 is equals to PL minus P naught by L, straightforward simplifications by applying these two boundary conditions in this pressure distribution equation, right. So, now if you substitute C1 and C2 here in this equation back, then you get P is equals to minus P naught minus PL by L z plus P naught, that is what you are going to get, or dou p by dou z is nothing but C1, that is minus P naught minus PL by L, that is minus delta P by L. So, dou p by dou z is nothing but a constant, that is minus delta P by L. Now, again now whatever the dou p by dou z is equals to dou tau yz by dou y is there, that equating to C1. So, now C1 is minus delta P by L, that means tau yz is nothing but minus delta P by L multiplied by y plus C3, get it, on integration. Now, we have to apply a boundary condition in order to get this C3. So, what is the boundary condition that we take? At y is equals to 0, at the center of these two plates, between these two infinite parallel plates, at the center point, that center point we have designated as y is equals to 0. At y is equals to 0, shear stress is going to be 0 and then velocity is going to be maximum. So, at y is equals to 0, tau yz is equals to 0. So, obviously the constant C3 is going to be 0. That means tau yz is equals to minus delta P by L multiplied by y. So, here also in this geometry also, when the flow is laminar and then fully developed flow, then shear stress is linearly varying in the y direction, Okay. Now, till this point what we have done? We have done simplifying of continuity and then momentum equations after having enough understanding about the geometry and then confinements or constraints of the problem. We got this expression, right. We have not applied any restrictions or assumptions about the rheology of the fluid, right. So, that means up to this problem, whether the fluid is power law fluid, whether the fluid is Newtonian fluid, whether the fluid is a viscoplastic fluid, whatever it is, as long as the fluid geometry fluid is generalized to Newtonian fluid. So, this expression is not going to change. So, the rheology of the fluid is coming into the picture from this point onwards. Okay. So, now this expression you can use in order to get the velocity profile. How to get that one? That all now depends on the mathematical simplification, depends on the rheology of the fluid and then subsequent mathematical simplifications. So, the flow is symmetrical about mid plane, that is what we have seen. So, that is that is whatever the flow is taking place between y is equals to 0 to y is equals to plus h, the same thing is taking place between y is equals to 0 to y is equals to minus h. So, in order to reduce mathematical simplifications, what you can do? You can take the flow between y is equals to 0 to h and then do the required simplifications. Okay. So, between y is equals to 0 to h, we take for power law fluids tau yz is equals to m minus dvz by dy whole power n. Why minus we are taking? Because at y is equals to 0, the velocity is maximum, and then at y is equals to h, the velocity is 0, vz is 0, here vz is maximum. And then as y increasing, what happens? The velocity is decreasing, right. So, that means you are going to have the flow profile something like this, let us say. So, that means as y increasing, velocity is decreasing, that means the velocity gradient is going to be negative. So, that is the reason here we have taken minus dvz by dy. So, that is shear rate is negative in this region between y is equals to 0 to y is equals to h, that is velocity is decreasing as increasing, that is the reason we have taken this one. So, now this tau yz is nothing but minus delta p by L y. So, minus delta p by L y is equals to tau yz. In place of tau yz, we have written m minus dvz by dy whole power n. So, now what we want? We want this velocity expression, vz expression is required. So, then vz term we are keeping one side, rest all other terms we are taking other side. So, that we have minus dvz is equals to minus delta p by L m whole power 1 by n y power 1 by 1 y power 1 by n dy. This is what we are going to have. Now, if you integrate this equation, we get minus vz is equals to minus delta p by L m whole power 1 by n y power n plus 1 by n divided by n plus 1 by n plus constant. So, now next step what we do? We both sides multiply by minus, so that we get vz is equals to minus of n by n plus 1 minus delta p by L m whole power 1 by n y power n plus 1 by n minus constant. Now, this constant we have to obtain. How do we obtain? We can obtain y is equals to 0, vz is equals to v max, that we can apply, or y is equals to plus h, vz is equals to 0, that also we can apply. So, what is v max or vz max we do not know. So, the better is you apply a boundary condition where you have the fixed known value as a boundary value. So, that is at y is equals to plus h, we have vz is equals to 0. So, then we get in this equation constant is equals to minus of n by n plus 1 minus delta p by L m whole power 1 by n h power n plus 1 by n. So, now this constant you can substitute here in this equation and then simplify, then you have this vz is equals to n by n plus 1 multiplied by minus delta p divided by L m whole power 1 by n h power n plus 1 by n multiplied by 1 minus y by h whole power n plus 1 by n. After substituting this constant here, what we have done from the both the terms, we have taken h power n plus 1 by n common. So, that we have 1 minus y by h whole power n plus 1 by n as within the parenthesis, right. So, this is what we get velocity profile, right. If you wanted to know the maximum velocity, in this expression if you substitute y is equals to 0, you get the maximum velocity, because at the center line, that is at y is equals to 0, velocity is maximum. So, vz max is equals to n by n plus 1 minus delta p by L m whole power 1 by n h power n plus 1 by n, fine. So, now we got the velocity profile as well as the maximum velocity. Now, we try to obtain the volumetric flow rate. Volumetric flow rate is nothing but integral 0 to h vz multiplied by w dy. W is nothing but width of the plate along which the fluid is extended in the x direction, as I mentioned while discussing the geometry. Then y is this 2 is multiplied, because we are the whatever the velocity profile that is there, that we got between y is equals to 0 to plus h only, but the volumetric flow rate we are getting for the entire geometry because it is flowing in the entire geometry. So, average whatever the volumetric flow rate is, that is what we are going to get. So, that is the reason, since y whatever the velocity profile is there, y is equals to 0 to y is equals to plus h, same velocity profile is there between y is equals to 0 to y is equals to minus h. So, that is the reason the velocity is multiplied by 2 here. Okay. So, now Vz you can substitute here. So, Vz is this expression, right. 2w is a constant. So, we take outside of the integration and then dy. So, if you do the integration, so this all these term before the parenthesis whatever is there, that is a constant term. So, only this part you have to integrate. So, when you do it, you get y, integral of dy is y. Then from the second term 1 by h whole power n plus 1 by n is a constant that you take common, and then integration of y power n plus 1 by n is nothing but y power 2 n plus 1 by n divided by 2 n plus 1 by n, and then limits 0 to h. So, when a lower limit is 0, so both the terms should be 0. So, when you substitute the upper limit here, so we have h minus 1 by h whole power n plus 1 by n, h power 2 n plus 1 by n multiplied by n by 2 n plus 1, right. So, this is what we have. So, now next step what we do, this whatever 1 by h whole power n plus 1 by n is there, that I am writing h power minus of n plus 1 by n, so that I can combine these two terms, or you can directly write h power 2 n plus 1 by n minus of n plus 1 by n, that you can do. So, then when you do that one, simplify it, you get it that this one. So, what you have here, h power 1 you are having. So, what you can take, so h minus h n divided by 2 n plus 1, from these two terms now you can take h common, and then if you do the LCM, so h multiplied by 1 minus n by 2 n plus 1 is nothing but n plus 1 by 2 n plus 1. This is what you are having here, right. So, now this h we combined with 2w. So, 2wh we will be having here, and then this n plus 1, this n plus 1 is cancelled out. So, then remaining term n by 2 n plus 1 we are having, the remaining two terms are as it is. So, this is the expression for the volumetric flow rate for a power law fluid flowing between two infinitely long parallel plates. Then average velocity if you wanted to get, if you divide this q by 2wh, you will be getting average velocity, that is average velocity is nothing but q by 2wh. So, that is n by 2 n plus 1 minus delta p by Lm whole power 1 by n h power n plus 1 by n. This is what we are going to have, right. So, now what we do, the same geometry, but we are going to have a different fluid, we are going to take a Bingham plastic fluid, right. So, now we have a Bingham plastic fluid. So, what we know that Bingham plastic fluids, they do not flow until and unless the applied stress is more than the characteristic yield stress of the material, that we know. So, now at y is equals to 0, this is y is equals to 0, the same geometry we are taking, same coordinate system everything. At y is equals to 0, what we have? We have the tau yz is equals to 0, right. At y is equals to h, at y is equals to h, we are going to have a maximum wall shear stress. In these two, between these 2 points, we know that the shear stress is linearly increasing, that is what we have already seen. So, that we know for the power law fluid, so that it is increasing like this. So, now what happens? So, let us say up to certain point, so at y is equals to 0, velocity is going to be maximum, and then at y is equals to h, it is 0, right. So, now shear stress is 0 here. So, gradually it increases, gradually it increases. There would be a point where tau yz whatever is there, that will become tau naught b, or characteristic yield stress of the material. So, that point we do not know what it is, where location we do not know. So, let us call this point is Hp, right, because now it is a Bingham plastic material. The velocity profile if you try to obtain for this one, So, up to this y is equals to hp point, y is equals to hp point is the point where up to which the material is flowing as a kind of a constant velocity plug. It is having a constant plug velocity, right. So, that is velocity profile is going to be something like this, and then within the limit of y is equals to 0 to y is equals to hp, it is going to a constant maximum plug velocity. After that only deformation starts, and then when the deformation is starting, as we move towards the wall, towards the top plate, the velocity is decreasing because of a no slip boundary condition at the wall, right. So, now what we have here, we have two velocity profiles, rather two velocity profile, one velocity profile which is function of y, and then another velocity profile or constant velocity VZP, which is not function of y, which is constant between y is equals to 0 to y is equals to hp, right. But from y is equals to hp to y is equals to h, deformation is taking place. Within that deformation region, velocity is function of y. That is what we are going to see now, right. So, now like in the pipe flow conditions we have done, here also in this geometry also we are going to develop the velocity profile for two regions. One is the non-deforming solid plug kind of region where the velocity is constant, that is VZP or VZ maximum. Another region where the deformation is taking place, where the material is flowing like a viscous fluid, not like a plastic solid. So, within that viscous fluid region or where the deformation is taking place, the velocity is function of y. So, the division of the flow geometry in two parts is the only difference here, because that is the characteristic nature of the viscoplastic fluids. Viscoplastic fluids does not flow as long as the applied stress is more than the characteristic yield stress of the material. Yield stress of the material is the characteristic of the material, like density, viscosity, etc., that characteristic of the material we are having in general. So, this yield stress also is a characteristic of the material for the viscoplastic material. So, now which we have to identify the location at which the applied stress is becomes equal to the yield stress of the material, right. So, that location we are calling HP, because we know that this tau yz is linearly varying in the y direction. We already seen in the power law fluid case. So, that does not change with the fluid nature, only velocity profile is going to change with the fluid nature, rheology of the fluid. Okay. So, between 0 to HP we are having constant plug like region where the material is flowing like a plastic solid material with a constant plug velocity, and then y is equals to hp to y is equals to plus h, we are going to have a kind of deforming region where the material is flowing like a viscous liquid, because in that region the applied stress is more than the characteristic yield stress of the material, right. So, for that region velocity is going to be function of y. So, these two things we are similar to kind of pipe flow things whatever we have taken, but we are now geometry is different. So, we have to define like this here again. So, now this is the basic understanding of the Bingham plastic fluids flow between two infinite parallel plates. Next is the whatever the assumptions, constraints, and then simplification of continuity momentum equation, they are going to be same. So, then we can have exactly same thing like in the power law case. So, these things are same: constraints, simplification of continuity equation, simplification of momentum equation, whether it is x component or y component, whichever component of momentum equation, the simplification is same. So, we are going to get the same outcome of simplification of this momentum equation, because the constraints are same, only the rheology of the fluid is changed. So, that is coming into the picture only after having the shear stress expression. So, the simplification of z component of momentum equation is also going to be same exactly like a power law case, because the geometry is same, constraints are same, flow constraints are same. So, the pressure distribution whatever we got for the power law case, the same thing is valid here also. So, shear stress also same thing is valid here. So, exactly same thing we get. Up to this point, the did we incorporate rheology of the fluid? No, not at all. So, up to this point, whether it is power law fluid or a Bingham plastic fluid, it is going to be same. Okay. So, now the fluid rheology will come into the picture through this tau yz part. Okay. So, we have seen the symmetric about mid plane y is equals to 0. So, between y is equals to 0 to y is equals to h, whatever the flow is taking place, distribution, whatever the distribution that we are going to get, the same distribution we are going to get between y is equals to 0 to y is equals to minus h, that is towards the bottom plate. So, what we do, we solve only in the off domain, so that to reduce mathematical listings, simplification steps we can reduce. So, then tau yz is equals to tau naught b plus mu b minus dvz by dy, that minus I have written before the mu b. Why minus dvz by dy? Because the same reason here also, from y is equals to hp to y is equals to h, as we are increasing the y, the velocity is decreasing from maximum vz or vzp or plug velocity, it is going to 0 velocity at the top plate y is equals to, which is located at y is equals to h. So, from y is equals to 0 to y is equals to h, when we are increasing, we are increasing the y value, the velocity is decreasing, that means shear rate is going to be negative. So, that is the reason we have minus here. So, now here again in place of tau yz, if you substitute minus delta p by Ly, and then that you equate to tau naught b minus mu b dvz by dy, right. Then we wanted to get the velocity profile. So, dvz by dy we are keeping one side, rest all terms we have taken to the other side, right. Next what we are doing, we are integrating it. So, here tau naught b y, here y square by 2 for the multiplication of minus delta p by L we get by integration, and then constant, right. So, now the boundary condition that we apply, that is again same boundary condition at y is equals to plus h, Vz is 0 because of the no slip boundary condition, and then constant you get minus 1 by mu b multiplied by tau naught b h minus delta p by L h square by 2. Now, this we substitute here. So, and then after substituting, what we are doing, we are combining the terms. This is the 1 by mu b tau naught b y minus delta p by L y square by 2 as it is, in place of constant minus 1 by mu b tau naught b h minus delta p by L h square by 2 we are having. So, now next what we do, we take or combine the terms which are having minus delta p by L terms and then tau naught b terms. So, when you combine these terms minus delta p by L terms, you can what you can have minus delta p by L h square by 2 mu b you can take common. So, when you do that one, remaining terms would be 1 minus y square by h square. Similarly, from the remaining two terms, if you take tau naught b h by mu b common, you can have 1 minus y by h as a multiplication, and then this velocity profile is only for the deforming region or where the region where applied shear stress is greater than the characteristic yield stress. So, that deformation is taking place and then material is flowing like a viscous fluid, right. So, that is between Hp to H only this equation is valid, right. So, but if you wanted to know the plug velocity, what you can do in this equation, you can substitute y is equals to Hp, because this equation is valid between Hp to H. You can substitute y is equals to Hp to get Vzp, right. So, that is what we are doing that one, that will give you the maximum velocity or the plug velocity. So, now plug velocity or maximum velocity is at y is equals to Hp. So, in the above equation, that is in this equation, wherever y value was there, so we substituted Hp in the previous equation. In the Vz expression, wherever y was there, we are substituting Hp, then we get Vzp. So, this is what we have. So, now what we have, further simplification of this equation we can do by taking this tau naught b as minus delta p by L Hp, because tau naught b divided by tau wall if you do, what you get? Tau naught b is minus delta p by L multiplied by y. In place of y you have the Hp, and then tau wall is nothing but minus delta p by L multiplied by H at y is equals to H. This is what we have. So, that means in place of tau naught b you can write minus delta p by L Hp, that is what you can write, because this tau naught, whatever the tau y z expression was there, minus delta p by L multiplied by y, this expression is valid between y is equals to 0 to H. So, when you substitute y is equals to Hp, that will become equal to the characteristic yield stress of the material. So, in place of tau naught b we are writing minus delta p by L Hp. Okay. So, that we have because of this relation, right. So, now what we do, why? Because this entire equation VZP equation we wanted to write in terms of the pressure, that is the only thing. Otherwise, this also we can after simplify and then take it as a final expression, right. So, now here what we can do, from these two terms we can take H square by 2 mu b minus delta p by L as a common term. So, then we have 1 minus Hp square by H square, this is as it is, remaining term minus 2 Hp minus 2 by H square Hb by H multiplied by 1 minus Hb by H you are having. So, now what we do, we expand this term. When we expand this term, what we will have? We will have like this is minus 2 Hp by H we are having, and then this is plus 2 Hp square by H square. So, there it is minus Hp square by H square is there. So, then plus Hp square by H square we are getting. So, this you can write 1 minus Hp by H whole square. So, that is VZP, we are going to get this expression, or Vz max is this one, that is H square by 2 mu b minus delta p by L multiplied by 1 minus phi whole square. Phi is nothing but Hp by H, which is nothing but tau naught b by tau w, which is not known a priori. For a given flow geometry, flow conditions, it is not known. So, because of that reasons, most of the problems associated with the viscoplastic fluids, we have done trial and error approach kind of thing that we applied, like Hanks model or Slater model. For the case of pipe geometry, we have applied, we have seen, trial and error kind of approach is required, or some kind of analytical expressions are required. Anyway, we think let us not worry about that one. So, phi is nothing but the ratio between the characteristic yield stress divided by the maximum wall shear stress, right. Tau naught b is nothing but minus delta p by L Hp, and then tau wall is nothing but minus delta p by L multiplied by H. That is, whatever this expression tau yz is equals to minus delta p by L multiplied by y. So, in place of y if you substitute Hp you get tau naught b, in place of y if you substitute H you will get the wall shear stress. So, that is Hb by H is nothing but tau naught b by tau w, that we are calling as phi. And this is valid between obviously 0 to Hp range, that is the non-deforming solid plug like material whatever is moving, like a solid plug, like a plastic plug. So, that material whatever that plug like velocity is there, so that is given by this velocity, and then this is valid only between 0 to Hp. So, volumetric flow rate Q is equals to 0 to H Vz 2W dy, that is what we have, right, from the geometry. But now Vz is having Vzp between y is equals to 0 to Hp, and then Vz from between y is equals to Hp to H. So, this Vzp, Vz we already got in the previous slides like this. So, now we substitute them here and then integrate. So, when you substitute Vzp this one here and then integrate, so this entire thing is constant because Vzp is a constant velocity, it is not changing with y direction, 2 and w are also constant. So, this entire thing multiplied by y you are getting after integration, and then limits are 0 to Hp. The remaining terms 2w, and then this entire term when you integrate it. So, here for the integration you are going to get y, and then here for the integration y cube by 3 you are going to get. So, that is here. So, then again here for integration, on integration you get y, and then here on integration of this y term you get y square by 2, that is here. And then this tau naught b we are writing minus delta p by L h p as we have done previously for the obtaining the plug velocity, right. So, that all the terms now are in minus delta p by L term, L form. Okay. Now, so these limits we substitute, so h p we are getting here. So, now here upper limit h you substitute, so you get these two terms, when lower limit h p you substitute, then you get these two terms, and then last term also when you substitute upper limit you get h minus h square by 2 h, lower limit h p if you substitute here, so you get minus h p plus h p square by 2 h. So, now from all these terms what we are trying to do, we are trying to take 2 w h square by 2 mu b minus delta p by L h as a common. So, then we are getting all these terms from the remaining 3 terms, right. Now, further what you do, you combine the terms, or wherever this h p by h is there, wherever this h p by h is there, by taking that h common you are getting this h p by h terms everywhere in all the 3 terms, right. So, in place of h p by h we are writing phi, here also we are writing phi, here also h p by h cube, h p by h whole cube we are writing phi cube, right. And then here also h p by h we are writing phi by 2, and then this is also h p by h is phi. So, phi into phi square. So, like that here also h p by h is phi square, and then this another h p by h we are multiplying. So, phi cube by 2, that is what we are having. Okay. Next step what we are going to do, we are dividing by 3 and then multiplying by 3, so that we can have some simplification. Okay. Then, so except this term we have 1, and then all other terms are being multiplied by 3. Here also it is multiplied by 3. So, 3 by 3 1 we are writing here. So, in the next step 1 we have written here, minus 3 phi by 2 we have written, phi cube by 2 we have written here, right. So, these 3 terms we have written here as the first 3 terms, and then whatever this 3 by 2 1 minus phi whole square by phi divided by 2 term is there, that we have written here, right. So, remaining 3 terms whatever are there, these 3 terms we can write them as if you take 3 by 2 common, we can write them as 1 minus phi whole square by whole square multiplied by phi, you can write these remaining 3 terms. We can write them as 3 by 2 1 minus phi whole square phi, that is what we can write. So, that this plus 3 by 2 1 minus phi whole square phi, and then minus 3 by 2 1 minus phi whole square phi can be cancelled out, so, right. So, that we have q is equals to this expression, only first 3 terms would be there. So, this is the expression for the volumetric flow rate, right. So, whether it is pipe geometry or parallel plate geometry, whatever, the methodology how to get the velocity profile, how to get the volumetric flow rate is same, as long as the flow is the laminar one dimensional flow, without any difficulty we can do. The same methodology we have to follow. So, now before winding today's lecture, quickly we take another geometry, inclined surface. So, let us say we have a inclined surface like this. So, this is the inclined surface, right. So, which is inclined to the horizontal axis at an angle beta. So, there is a material is coming and then flowing down here because of the gravity, right. The thickness of the material that is flowing down is h, okay. Inclined surface on which the material is flowing, that inclined surface flow direction we are taking z, the other direction we are taking y. So, here also Vz is function of y compared to the Vz, other Vx, Vy are going to be 0, right. So, what is this velocity profile as function of y, we have to get it. So, now here the gravity, it is not either completely horizontal, it is not either completely vertical. So, it is in inclined surface, inclined at beta angle. So, then whatever the 2 components are there, so if it is g is acting in this direction, if you draw the tangents, so this direction we are going to have g sin beta, and then this direction we are going to have g cos beta, right. So, now what we do? We do these simplifications, right. We write the constraints of the problem, right. We are taking the steady state, incompressible and as isothermal flow conditions, laminar flow, only Vz is existing and then Vz is function of y. This material whatever is flowing down, it is very thin actually. The thickness of the material is very thin. Within that thin layer of the material, how the velocity profile is varying. So, for such thin layer of the material that is flowing down, so it is only one component is going to be predominant, other components are going to be 0. That is in the vertical direction or in the x direction, we are not going to have any velocity. So, Vz is only existing, Vx, Vy are going to be 0. So, here also Cartesian coordinates are applicable. So, then continuity equation if you apply here. So, what we have steady state. So, this is 0, Vx is 0, Vy is 0, right. Vz is not 0, but whether the material is under fully developed flow conditions or not, that also we do not know. That is the reason dou by dou z of rho Vz we cannot cancel out. So, what we get from simplifying the equation, dou Vz by dou z is equals to 0. So, what does it mean? For this flow geometry, when you apply these constraints, you get another a constraint, that is the flow is fully developed flow constraint that you can understand through the continuity equation. Remember, as we have been discussing, that the importance of continuity equation, simplifying the continuity equation is that whether the constraints that we are taken, they are consistent or not, that is what we can understand. Otherwise, if some boundary conditions or some kind of limiting conditions we are not or some kind of constraints we are not very sure from the problem geometry, then such kind of constraints we can get by simplifying the continuity equations. So, that is what we are doing here, that is what we get here. We are not sure from the geometry whether the flow is fully developed or not, but from the continuity equation or by simplifying the continuity equation, what we understand, dou Vz by dou z is equals to 0. That means, the flow is fully developed in the z direction. Similarly, now x component of momentum equation if you simplify, so Vx is 0. So, then all the terms in the left hand side are having Vx terms because it is x component of momentum equation. So, all of them are 0. Pressure we do not know, and then only tau yz is existing. So, these tau expressions are 0, and then gravity in the x direction, whatever the gravity we are taking, that is not there in the x direction, it is there only in the y and z directions. Okay. So, what we understand from here, dou p by dou x is equals to 0, that means pressure is not function of x. Similarly, y component of momentum equation if you simplify, then steady state this term is 0 and then Vx is 0, Vy is 0, Vz is not 0, but Vy is 0. So, that is 0. Pressure we do not know anything. This only tau yz is existing, but this is not existing, tau xy, tau yy are not existing. Tau yz is, or tau zy is existing, but because of the fully developed flow condition that we get from the continuity equation, this term is also 0. Rho gy in the y direction, gravity is nothing but g cos beta. So, what we get, dou p by dou y is equals to rho gy from the y component of momentum equation, that is nothing but rho g cos beta. Similarly, z component of momentum equation, steady state, this is 0, Vx is 0, Vy is 0, Vz is not 0, but from the continuity equation we understand that dou Vz by dou z is 0. So, this is 0. So, next pressure, the flow is taking place only because of the gravity. So, then whatever the pressure distribution in the z direction is there, that also we can take it as a 0, and then tau xz is not existing, tau zz is not existing, tau yz is existing, tau yz is existing, and then it is function of y also, because whatever the thickness of the fluid is there, that is expanding in the y direction. So, from y is equals to 0 to y is equals to plus h, the shear stress is varying. So, that component you cannot cancel out, and then gravity in the z direction is existing. That means, dou by dou y of tau yz is equals to minus rho gz, that means minus rho g sin beta. So, once we have this tau yz expression, rest everything is a simplification to get the required velocity profile. Okay. So, from this z component of momentum equation simplification, whatever dou by dou y of tau yz is equals to minus rho g z we got, from there we can get the tau yz expression as tau yz is equals to minus rho g sin beta y plus C1, because Gz is nothing but g sin beta. Okay. So, what we get, tau yz is equals to minus rho g sin beta y plus C1. This C1 constant you can get by applying the shear stress boundary conditions. Tau yz is equals to 0 at upper surface, at y is equals to plus h. Upper surface of the fluid layer we are calling y is equals to h, and then tau yz is equals to maximum or tau wall at y is equals to 0, because now unlike the previous geometry or pipe flow conditions, the fluid is at the surface, the inclined surface, the material is flowing down. So, at the inclined surface what we have, the maximum wall shear we are going to have the maximum wall shear stress at the along the inclined surface, and then this region the material is flowing down. So, the upper layer of the fluid whatever is there, that is open to the atmosphere. So, then that y is equals to h is going to have a 0 shear stress. So, that boundary condition we apply, that is y is equals to h, tau y is equals to 0. So, C1 is equals to rho g sin beta h. Then if you substitute that one here in this equation, you get tau yz is equals to rho g h minus y sin beta. So, tau yz is equals to rho g h minus y sin beta. Once we have this expression, so you can apply next step rheology of the fluid to get the velocity distribution. So, for this geometry what we are doing, we are taking Ellis model fluid. Ellis model fluid tau yz is this one, this we already know. So, this expression we rearrange so that we get mu naught dou Vz by dou y one side, another terms are other side. So, then what we have, dou Vz by dou y is equals to 1 by mu naught multiplied by tau yz plus tau yz power alpha divided by tau of power alpha minus 1. So, this alpha and then tau of, we already know this characteristics of a LS model fluid. So, now what we do? In this expression, dou Vz by dou y is equals to 1 by mu multiplied by tau yz plus tau yz power alpha divided by tau of power alpha minus 1. This is coming only from the rheology of the material. Whatever the rheological expression for the LS model fluid is there, only from that only we got. Now, for our problem, what is tau z? For our this flow problem, what is tau yz? That we already got, that is nothing but rho g h minus y sin beta, that we are going to substitute. So, when you substitute here this one. Now, when you integrate this one here, h y minus y square by 2 you get, here you get h minus y whole power alpha plus 1 divided by minus alpha plus 1 you get, minus of alpha plus 1 you get here. Rest all other terms are constants, right. So, now apply the boundary condition to get the constant C. So, at the wall, that is at y is equals to 0, Vz is 0. So, then this constant is nothing but this one. In this equation, if you substitute y is equals to 0, then Vz would be 0, left hand side would be 0. So, then constant you get this one. So, this constant you substitute here and then simplify, then you get velocity profile like this. So, simple simplification only, just rearrangement I am writing directly here. So, the volumetric flow rate Q is equals to integral 0 to h Vz w dy. W is nothing but the width of the fluid in the x direction that we have seen in the geometry. So, this Vz expression we got this one already, and then if you integrate this one, you get here for this place y square by 2, and then for this point you get y cube by 3 on integration, and then here this part you get y, and then here what you do before integration, what you do here, this term you do the LCM, so that you can have h minus y divided by h, so whole power alpha plus 1. So, h minus y whole power alpha plus 1, if you do the integration, you have h minus y whole power alpha plus 2 divided by alpha plus 2, right. Then whatever that h power alpha plus 1 is there, so that you have taken common here. So, that is what we are getting this one, right. So, now the limits 0 to h also if you substitute and then simplify, so you get this thing, straightforward simple simplification that you can do it. So, this is the volumetric flow rate Q by W is equals to given by this expression if a LS model fluid is flowing down along the inclined surface. So, finally, example problem. So, the material of density 1000 kg per meter cube is flowing down on a wide inclined surface at angle beta is equals to 30 degrees. The fluid thickness, as I said, the fluid is in general very thin. So, 3 mm thickness only there. The rheology is defined by the Ellis model fluid. So, that we have the mu naught, tau of and then alpha are given. Right. So, we have to find out the volumetric flow rate. So, we just developed Q by W is equals to this expression. So, in this expression in the right hand side everything is known, rho, g, h, beta, mu naught, alpha, tau of everything is known. So, when you substitute and then simplify you get 6 multiplied by 10 power minus 4 meter cube per second per unit width of the plate. So, that is the volumetric flow rate. Okay. References: the entire lecture is prepared from this excellent book by Chabra and Richardson. Other reference books are provided here. Thank you.